Okay, so lesson 6.1, approximating area with Riemann sum. This will be our last page. Example number 6. The table below represents the velocity v of t in feet per second of a car traveling on a straight road over a 50-second time interval. We want to estimate the distance the car traveled over this interval using RRAM and LRAM. They call it RHS. I call it RRAM. They call it LHS. I call it LRAM. So RHS is RRAM and LHS is LRAM. Okay? So right-hand Riemann sum and left-hand Riemann sum, along with two different approximation techniques, the midpoint and trapezoidal rule. Use the table along with the graph for your computation. So we're going to estimate the total distance traveled by the car by using the left-hand Riemann sum method, L5, so mine will be LRAM5, with 5 partitions of equal length. Show your setup and draw the rectangles on graph number 1 in blue. So we are going to take our 50 minus 0 divided by 5. That's my b minus a divided by n. So my b was 50, my a was 0, because that's my closed interval AB, my closed interval from 0 to 50, and they wanted us to have 5 of those rectangles, or 5 partitions. And so 10 is my delta x. So we've got our delta x equal to 10. And we're supposed to be in blue, sorry. I'm going to change to blue right now. So now, I'm going to mark off where those partitions will be. And since we're doing LRAM, I have to either choose this point or this point for this first rectangle here. We can see that the height of, or the width of this rectangle is 10. If I choose LRAM and go this way, I'm going to have 0 here, right? That's my LRAM. This is my left hand. This is my right hand. So for the first one, if I'm doing my LRAM 5, they're all going to have a width of 10. So instead of doing 10 times this, plus 10 times this, plus 10 times this, I'm going to factor the 10 out, and I'm going to just add all of my height values. Now it's between this point and this point. This one is my LRAM. So I'm going to use that value at 10, and I see it's 20. So that's 10 times 20. Okay, here's my LRAM for the next one. Here's my RRAM. I'm going to use LRAM, and that's going to be the area that I'm talking about. And I'm going to look up here in my table and see that I have 52 in my table at 20. And then I've got my L and my R. I'm going to do L, and this will be my rectangle. So I'm going to use my value at 30, which is 80. And I've got, again, LRAM and RRAM. I'm going to use L. And this will be my rectangle that I'm using for my approximation. And that is my value at 40, which was 77. So this is 10 times 229, which is 2,290. And remember that if you're in feet per second and your per sec and the seconds cancel, you are left with feet here. So this is 2,290 feet. If my y-axis is a rate, the unit will be the numerator unit of my y-axis's rate. That is what the rate, or the unit will be for my answer to my area under the curve. Now we're going to use the right-hand Riemann sum with 5 partitions. So this is going to be our RAM 5, and it's 5 partitions also, so it's going to have the same delta x equals 10. So we've got our 10 here, and this time we're going to choose the right-hand side, and then we're going to use that to find our area of our rectangle. So I'm going to use the function's value at 10, which is 20. And then I'm going to use the right hand and calculate that area. So that one is the function's value at 20, which was 52. And then the right hand would be for the next one, the function's value at 30, which we see as 80. And then the right hand, which is our function's value at 40. And our function's value at 40 is 77. And then we use the right hand, which is our function's value at 50, which is 74. So this is going to be 10 times 303, giving us 3,030. And again, that would be feet. So the actual will lie somewhere in between here, because we knew that our LRAM gave us, an underestimate while it was increasing, and it gave us an overestimate when on its decreasing portion. And then our RAM gave us an overestimate on the increasing and an underestimate on the decreasing portion. So part C. Next, use the midpoint sum with 5 partitions. The first rectangle is shown in graph number 2. Show your steps. So this time it looks like they might want us to do green. So I'm going to get my green going again and see how the midpoint would be at 5 here. And so your midpoint here is going to be at 15. So you're just going to follow that midpoint point across, and you're going to calculate that area. And then the midpoint here is at 25. And so that's this one. And you'll follow it across, and you're going to calculate the area of that rectangle. Here's your midpoint here at 35. And you'll bring that across and down. And that's going to be the area of that rectangle. And then the midpoint here, follow across and down. And that's going to be that rectangle. So this is going to be MRAM 5. Again, your delta x is 10, because look, the width of it is 10. Even though you're picking 5, you're picking that midpoint, the width of the actual rectangle here is 5. Is 10. Oh my goodness. So this is actually 10, and then the function's value at 5 is going to be the height of your rectangle. And we can find out what that is by looking up at the table. But we're going to say 10 times, and at 5 we had 14. At 15 we have 28. At 25 we have 70. At 35 we have 86. At 45 we have 70. So this is going to be 10 times 268, giving us 2,680 feet. As our approximation using MRAM. So we had the 2290, which was an underestimate. We had the 3030, which was an overestimate. And then we have the 2680, which is closer to your actual than the other two. And you can see that it's right in between those two. So it's going to be closer to the actual. There's less error in that one, in that midpoint formula one. So now use the trapezoidal sum with 5 partitions. Show your setup and show trapezoids on graph number 2. So I'm going to use a different color here. I'm going to use a pink or a red. Maybe I'll use red. And what you would do here is you still use your L and your R, only you are connecting them like that, like a trapezoid. Now for this first one, your base 1 is 0. Base 2 is, you know, whatever the function's value was at 10, 20. But look how you are attaching like that to make that trapezoid. Okay? So you're attaching this one to this one. So you just connect, and then you've got a trapezoid. So you're connecting this one and this one over here. And there's your trapezoid. You're connecting this one and this one over here. So you're connecting your left and your right and just straight connection, and you're making these trapezoids. And just to remind you what the trapezoidal rule is, the area of a trapezoid is height divided by 2 times base 1 plus base 2. And so now we've got the height is the same. It's 10 for every single one of these. Remember, this is your height. 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 It's 10 for every single one. So I know that they all share that height of 10. And this is trap. We usually call it trap 5. So this is our height divided by 2. Now, I'd like to tell you that you're going to use your base 1 one time. And your base 1 on this one is 0. But you're going to use your base 2 twice, because it's going to be the base 2 for the first one. It's going to be the base 1 for the second one. So your value at 10, which was 20, is going to be used twice. Also, the one at 20 is going to be used twice. It's going to be the base 2 of the second trapezoid, and it's going to be base 1 of the third trapezoid. So we're just going to say twice 52. The one at 30 is going to be used twice. It's going to be the base 2 of the third trapezoid, and it's going to be base 1 of the fourth trapezoid. So at 30, we have 80, and that's used twice. At 40, we also are using that twice, because it's base 2 of the fourth trapezoid, and it's base 1 of the fifth trapezoid. So at 40, we had 77, so that's 2 times 77. The one at 50 is only used once, because it's only the base 2 of that last trapezoid. So we're able to just say plus 74. So this is kind of like our trapezoidal sum. Notice that you're using the, this is like your f of A, and this last one, 74, is like your f of B. So you're using, you know, you're using the very first one and the very last one. And then every single one in between is multiplied by 2, because you're using it as base 1 and base 2. So if we simplify this, we get 5 times 532. And that's going to give us 2,660 feet. And there's very little error in this one. So if we found LRAM 5 plus RRAM 5 and divided it by 2, 2290 plus 3030 and divided it by 2, we get the 2660 or 2660 feet. That is the same as the trapezoidal 5. So I said that MRAM was the average of those two. I was wrong. It was trap that was the average. I'm so sorry. MRAM is just itself. It is a very good approximation. MRAM is. It's a very good approximation using rectangles. Okay. So please let me know what I can do for you to help explain this better. I'm having a little bit of trouble with my Google Hangout and my Zoom. But if you email me, I promise to try and maybe get your cell phone number, and maybe we can FaceTime. I don't mind doing that. That seems to be working better. I did that with Jana Bemis this morning, and it worked better than my Google Hangout did. I'm just having so much trouble with it, and I'm so sorry about that. I'll try and look at some of the homework problems and maybe put something on there with a few of the homework problems. But I want you to notice that when you go back over this lesson, let's scratch this out because I was wrong about that LRAM plus RRAM divided by 2. So go back up there on that page and scratch that out because your MRAM is just a very good approximation. It ends up being that trapezoidal is the LRAM plus RRAM divided by 2. Notice that we had a function and a picture here for that one. Here we just had a picture. Well, no, we had a function and a picture. Here we just had a graph picture. And here we just had a table. So we did this finding the area under the curve using all kinds of different methods. So, but mostly the thing that I want you to remember is that it is just an estimation for the area under the curve. It is not the exact area.